In the world of networking, we're all about redundancy. We want backup links, backup switches, anything to prevent an outage. But what if I told you that the very thing you add for safety, that extra cable, could be the thing that brings your entire network crashing down? Today, we're going to pull back the curtain on the unsung hero that prevents this digital chaos, the spanning tree protocol. So, here's how we're going to break it all down. First, we'll tackle the redundancy paradox, this weird idea that more can sometimes be less. Then we'll witness the chaos of a broadcast storm up close. From there, we'll see how order gets restored through an election, how a loop-free network is logically built, and finally, how a switch port safely gets in on the action. All right, let's kick things off with the fundamental problem that Spanning Tree was created to solve. I'm talking about the redundancy paradox. It sounds completely backward, doesn't it? You're doing the right thing. You plug in an extra cable between a couple of switches, thinking, great, now I have a backup path. But instead of getting that sweet, sweet high availability, the network just dies. The whole thing melts down. So what on earth is going on here? Well, this is where we hit a major conflict. The goal is awesome, high availability. But the reality of Layer 2 Ethernet exposes a massive weakness. You see, unlike the IP protocol at Layer 3, which has a handy little time-to-live counter to kill off packets that get lost, Ethernet has nothing like that. There's no kill switch. A frame that gets into a loop can literally circle between switches forever, creating copies of itself until the entire network just gives up. So what does it actually look like when a network gives up? Well, that leads us straight into the most catastrophic symptom of a Layer 2 loop, something we call a broadcast storm. Imagine one device sends out a single broadcast frame. A super common one is an ARP request. It's just a device asking, hey, who has this IP address? But in a looped network, that one simple question doesn't just get answered. It gets echoed and amplified and repeated, turning into an endless, deafening scream that eats up all the bandwidth and completely paralyzes every device trying to listen. Let's watch how it starts. A PC sends out just one broadcast. Switch 2 and Switch 3 both get it, and they do their job. They forwarded out all their other ports. This means they send it to each other. Now there are 2 copies looping around, and those 2 become 4, then 8, then 16, and within seconds, you've got a full-blown digital hurricane. And the fallout from this is just devastating. The switch's MAC address tables become totally unstable. They're seeing the same device pop up on different ports at the same time, which completely confuses them. Their processors get pegged at 100%, trying to handle the flood of traffic, and the end result? A total network outage. Nothing gets through. Okay, enough chaos. How do we stop this madness from ever starting? Well, we need to bring in some law and order. We need a traffic cop. That's Spanning Tree Protocol. And its very first order of business is to create a clear hierarchy by holding an election. You see, every switch has something called a bridge ID, or BID. Think of it as its number in the election race. It's made of 2 parts, a priority value and the switch's unique MAC address. And the rule for winning is incredibly simple. The switch with the absolute lowest bridge ID wins. That's it. Lowest number is the boss. So how do they actually run this election? They send out these special little messages called Bridge Protocol Data Units, or BPDUs. Each switch basically broadcasts its own ID saying, hey, I'm the leader. At first, they all think they're the boss. But as they start hearing the BPDUs from their neighbors, they quickly figure out who really has the lowest ID in the whole network. And if you look at this table here, the result is a total landslide. Switch 2 and Switch 3 are using the default priority, but someone went in and configured Switch 1 with a much lower priority of 24,577. It's not even close. S1 wins the election hands down and becomes our one and only root bridge. We don't even need to look at the MAC addresses to break a tie. Okay, so we have a leader. We have our root bridge. Now the network can start the next phase, building a single, logical, loop-free roadmap. The goal is to create one clear path from every point in the network back to the root, just like the branches of a tree all lead back to the trunk. This whole thing happens in 4 elegant steps. We've already done step 1. We elected the root bridge. Next, every other switch is going to figure out its single best path to the root. Then, for every link, we'll pick the best port. And finally, the most important part, any path left over gets blocked. That's how we kill the loop. This brings us to the root port. So every switch that's not the root, like S2 and S3 here, looks at all of its connections and asks, what is my fastest, cheapest path to get to the root bridge? The cost is usually based on link speed. Faster links have a lower cost. The path with the lowest total cost wins, and the port on that winning path is crowned the root port. It's that switch's personal highway to the root. Okay, next up, for every single cable that connects two switches, one side of that cable has to be elected the designated port. This is the port that offers the best path back to the root bridge for that specific link. It's basically the boss of that segment, responsible for forwarding traffic onto it. And here it is, the magic step, the grand finale. Take a look at port fast 0/2 on switch S3. It's not a root port, it's not a designated port. It's the leftover, the redundant path we wanted for backup. So what does Spanning Tree do? It logically puts that port into a blocking state. The physical cable is still there, ready to take over if another link fails, but for now, no data traffic can pass through it. The loop is officially broken. But hold on, a port doesn't just instantly flip from blocking to forwarding. That would be super reckless and could actually create a temporary loop while things are recalculating. Instead, a port goes on a very careful, deliberate journey through a sequence of states. The classic spanning tree protocol has 4 main states. It all starts in blocking, where a port just listens to the network's BPDUs but doesn't send anything. If it finds out it has a role to play, it moves to listening to help decide its role. Then it enters the learning state. This is where it starts building its MAC address table, but still no user data is sent. And only after all of that, a process that takes about 30 seconds, does it finally transition to forwarding and become fully operational. And that really is the essence of it all. That's the whole genius of Spanning Tree Protocol. It takes a messy, physically looped network that you built for redundancy, and it imposes this clean, predictable, and most importantly, safe logical tree structure right on top of it. It's all about bringing predictable order to potential chaos. But here's a final thought for you. This algorithm was invented way back in 1985. That 30-second delay to recover from a failed link might have been fine back then, but in today's networks, that's an absolute eternity. So it really makes you wonder, right? How has this ancient foundational protocol evolved to keep up? Well, that's where newer versions like Rapid Spanning Tree Protocol come into play. But that's a story for another time.